So, good afternoon, good morning, and good evening, everyone, depending on which place of the world are you watching us. My name is Henri Ormus. I'm Vice President of European Nuclear Society, currently working in Fennovoima in Hanhikivi 1 nuclear power plant project where we build a large-scale nuclear power plant in Finland. And also I'm a co-founder of Fermi Energia, and I will be leading this discussion. I'm very glad to have here online with us Alan Woods, Director Strategy and Business Development at Rolls-Royce, Brett Kungelmas, Managing Director at Energy Impact Center, David Sledzik, Senior Vice President Sales at GE Hitachi Nuclear Energy, and Mark Mitchell, President at USNC Power, and Scott Rasmussen, Director of Sales at NuScale SMRs. Welcome, everyone. First of all, we will have a short introduction and overview of their respective designs and developments, and then we will head to the questions. So, Alan Woods, please, could you give us a little overview?
Sure, yeah, let me just see if I can share a single screen as well. Please let me know if this is showing. Can you see my screen?
Yes, wait.
Yes, okay, great. So, quick overview of our technology, and then I'll talk about where we are with our program. So first of all, our technology really encompasses exactly what we're trying to do here and why we embarked on this program 5 years ago. For us, our technology, our SMR program, is about delivering nuclear at low cost at a competitive market cost. So yes, we use improving technology where we can. We don't want to introduce technologies which we know are going to be challenges to regulators or to operators. It's about simplification, standardization, and producing a factory fabricated product which is repeatable. That gives us a certainty in deliverability and a repeatable deliverable solution which we know we can meet our timeframes and costs with certainty. And all of that in around makes our product investable to any form of customer, whether it be a utility seeking to attach this to a grid, or whether it be an industrial customer wishing to use our SMR for desalination, for hydrogen generation, for synthetic fuel production, for data centers, or for other heavy industrial electricity uses. So our approach to modularization is, as I mentioned, all about standardization. We have to address the whole power station. This isn't a reactor design project. This is a power station development program. It's about moving from very large one-off mega infrastructure projects to a factory repeatable product. So 90% of our power station is factory fabricated. That includes the civil structures, includes all the balance of plant systems, and of course the nuclear reactor part as well. It sits on an aseismic bearing to insulate it from the particular site conditions, and that's very important for repeatability. It means all of our modules are the same no matter where we build the plant, and that means we properly get that factory learner curve for those road transporter modules. They come to the site, and we make use of our small footprint to assemble under what we call a site canopy, or our fourth factory. That is assembled and disassembled after the commissioning period. It's reusable, so it does have a cost, but we can use it 3 times. And that means that we assemble all the modules in a controlled environment. It takes us 4 years to build the plant on site, take down the site canopy, we finish commissioning it, and then it goes into operation. So that's our power station. Where we are at the moment, we're just completing the current phase of activities we're in, which has been a joint investment with UK government and our consortium partners. The UK Prime Minister announced in November the 10-point net zero plan, which included 250 million funding for the next phase of our program. That will be matched by industry and some of our partners, and we will in turn set up a special purpose vehicle company. So the next phase of our program will be to move all of the activity into a joint venture company. We will then enter genetic design assessment in the UK around Q3, Q4 this year. And of course, we will continue to support our customers in their ambitions and programs, both in the UK and internationally. So that's my brief intro. I hope I stuck to the few minutes. I shall stop sharing.
So let's continue with Brett, who will give an overview about the Open 100 SMR status and developments. Brett, please.
Great. Thank you, everybody, for having me. My name is Brett Kugelmass, and I'm the Managing Director of a Washington, D.C.-based research institute called the Energy Impact Center. So we spent years, 3 years now, meeting with experts across the nuclear industry, trying to figure out, we've got this magical technology, why isn't it more prevalent? Why is it remain stagnated at 10% of global energy production? It's emissions free. Countries have shown that they can scale up and totally decarbonize their entire grid. It's abundant. Like, why not more? And what we found is the primary reason that we don't build more nuclear around the globe today is because it is too expensive. And the reason that it's too expensive, and this is important, is because we, the nuclear industry, makes it more complicated than it needs to be. So we asked ourselves, what is the simplest possible nuclear power plant that can be built based on historical evidence? And so we assembled a team of fossil engineers that had built hundreds of power plants over their career. And we had them design a 100 megawatt biomass plant and just replace the boiler with the simplest possible nuclear reactor, which is a PWR, the same technology that operates in 300 power plants around the world today. And then we published all of our engineering work for public consumption, and I'll show you that right now. So anyone can go here. If you just go to www- or open-100.com, I should say, www.open-100.com. And you can see here the engineering all laid out. You can go into systems and pull up different systems diagrams, download all of the engineering work that you would need. You can pull up equipment and download CAD files, or even reach out to vendors that we've pre-categorized for you. You can pull up an economic workbook where you can see the power plant costs down to the line item. And you can even pull up a construction schedule where you can see line by line exactly the time and work that needs to be done to bring one of these small 100 baby normal standard PWR plants together in under 24 months. So our basic concept here is that the nuclear technology does not need to be proprietary. We do not need a bunch of vendors leading the way, trying to sell complicated and expensive reactor systems, and then trying to figure out how to build a power plant around it. We just need the most simple, straightforward approach possible. And so we've published all of this work totally free, so hundreds of utilities and developers can just start building this all on their own. And then we would just help from a financing and management perspective. So that's a brief overview, and I look forward to hearing more questions. Thank you.
Thank you, Brett. That's a pretty amazing job that you have been doing. Thank you. So let's move on with David Sledzik, who will present the status about the BVR X300. David, please.
On where you are in the world. My name is Dave Sledzik. I'm the Senior Vice President of Sales for GE Hitachi's new plant business. At last year's conference, I was able to share some information on our SMR. Lots happened in the last year, and I'm going to give you a quick refresher on the technology before I get into what we've accomplished in the last year. The BWX300 is a 300 megawatt SMR and is the most cost competitive SMR design out there in the marketplace. It's a great option for not just electricity production, but district heating, hydrogen generation, and other industrial applications. We've taken an innovative approach to take cost out of the reactor, but also maintain plant systems and components from our existing licensed fleet. And that reduces your major licensing hurdles. In addition to that, a lot of these materials like the fuel and some of the components do not require further testing for licensing because they are operating in our fleet today. So moving on to developments in the last year, along with our arrangement with Fermi, we're continuing to strengthen that relationship. We look forward to working with them further in this year into their endeavors. In the Canadian market, we were one of 3 technologies chosen to move into the competition. This was announced last October. Since then, we've set up an office in Canada, hired a director of our Canadian operations, and are working with OPG in the final stages of their selection process. In Poland, we've further developed our partnership with Synthos Green Energy and are working with them in the deployment and understanding of our reactor and how it fits into the Polish energy system. We also signed an MOU with ČEZ about the same time last year as we are right here today. And we know that this year they're going to move forward in working on SMRs and how that fits into their licensing regime. So we're excited to move forward with that. In regard to licensing, as you'll see on the screen, we started to submit licensing topical reports, or LTRs, to the US NRC. The first one was approved in 9 months, which is a pretty good record for the NRC to approve one. And that is really our secret sauce in driving the cost out of this reactor. It's an integrated isolation valve into the reactor pressure vessel. This eliminates all the safety systems, backup systems, concrete rebar. It really takes about 50% of the construction costs out of that reactor. Okay. We've also submitted 2 other LTRs. That one was approved by the NRC. The other one last week. We just got unanimous ACRS approval for that. We've submitted another 2 that will be approved before the end of the year. In Canada, we've submitted the first 2 packages of our combined phase 1 and 2 VDR. We're answering RFIs right now, and the 3rd package will be submitted in May. In Poland, we've started to work with Synthos and Exelon, and first discussions with the regulator there to discuss the steps in regulating the BWX300 in the Polish market. We're excited to move forward with that. If you think about our technology and GE and Hitachi, we have centuries of delivering energy solutions to the world, to modernize the world. We've got 60 plus years of experience designing, deploying, fueling, servicing reactors across the globe. We've licensed reactors in 10 different countries. So that type of experience and depth really is the genesis behind our 10th generation boiling water reactor. It builds on those decades of real world deployment and how we operate reactors today. Thank you.
Thank you very much, David, for your good update. So let's move on. Mark Mitchell, please present us the USNC micro modular reactor. Mark, we don't hear you. Still don't hear you. Could you try to unmute?
Henry,
yes,
USNC
now
is
we
a leader in the microreactor field with proprietary technology in microreactors, advanced fuel, and space reactors. My name is Mark Mitchell, and I am responsible for, as president of USNC Power, for our commercial reactor programs. I thought, as an introduction, I would share just 2 points with you. So the first is a bit on our progress, and the second is a little bit on our product. Since 2014, USNC has been progressing steadily towards deploying the first commercial Gen 4 reactor. This is really shown by our MMR at Chalk River Laboratory in Canada, which we're executing in partnership with Ontario Power Generation. We call this the Global First Power Project, and it's making progress towards securing all the necessary licenses and preparing for production. We expect to have the plant operational in line with the Canadian Nuclear Laboratory target date of 2026. On our product, this is a representation of our launch product, which we call the MMR Energy System. It's a small, it's a microreactor-based solution for off-grid applications. And if anyone's interested, in the bottom corner of the screen here, you can scan the QR code and get access to an AR app, which will enable you to explore the plant a little bit more. Some interesting facts about its features. It's a 5 megawatt electric equivalent design. It runs 20 years of life on a single fuel load. It uses proven high temperature gas-cooled reactor technology, combined with our proprietary fully ceramic microencapsulated or FCM fuel and molten salt energy storage. It's set up, it's designed to provide power to remote communities and industry, either as part of an islanded microgrid or an industrial integrated energy system. And to give you an idea of the scale, this is really quite small. Everything you see in this picture will come to site on the back of trucks and be assembled. We're targeting initial deployment in Northern Canada and also looking forward to later deployments, offsetting carbon emissions in industry and perhaps even moving towards other applications like hydrogen generation, as was discussed in the last session. So thank you very much for the invitation to join the panel. I look forward to the discussion.
Not least, Scott, could you give us, please, an overview of NuScale developments?
Sure, I certainly can, and thank you. And I'm so happy to be here. I couldn't be here last year, so I'm glad to be here this year. And appreciate the comments from my colleagues. It's exciting to see multiple SMRs kind of technologies be discussed and kind of come together here. And NuScale is at the forefront of the SMR industry, and it's good to hear there's so many similarities and we're all progressing well. That's very exciting. So I'm glad to be here. I want to give a little bit about NuScale and trying to go forward and talk about us just a little bit. Our total mission was to focus on bringing improved nuclear technology to the world, with the 4 pillars of our design being a smarter, cleaner, safer, and cost-effective design. Oh, and I just want to warn you, I have like 100 slides, but I'll only go through a few. One of the first things I get asked, and I was asked before this conference, was, so what's new with NuScale prior to, before we come to the conference? Well, NuScale has been very busy over the last, few years, since like 2007, developing our technology and moving forward with getting it licensed. Our technology design, the NuScale power module, and the base design of the NuScale power plant, which includes 12 power modules, was approved by the US NRC in August of 2020. The important part of that is not just getting a license for SMRs, it's working through that whole regulatory process and bringing a tried and true methodology forward so that it can address SMRs and understand how to really manage the differences between the large plants and the small plants and set up the entire industry for success. It takes an awful lot of due diligence and an awful lot of work to progress the design to be at that point, and we've done that. I love showing these statistics, but I really don't like talking about them. It gets old. On the smarter side, just like we've talked about, I think I heard Brett talk about the PWR technology, which is an excellent technology, and they all are, that we've leveraged that, and we basically said, how can we take this existing technology and really kind of bring it down into a similar format like Alan was talking about, that can be factory produced, shipped to site, and installed in a short period of time. We've done that. We're going through manufacturing trials and working through with multiple manufacturers to produce the NuScale power modules. Here's a cutaway view of showing how the modules fit into a plant. I did mention our basic design was approved for 12 modules, and we've been working on plant designs that include a 4-module plant and a 6-module plant to really meet the market needs. And I think that's the overall importance of SMRs, is figuring out what the market requirements are, not just regulatory requirements, but the commercial requirements, and trying to bring that forward and go from there. And you can see down below, the footprint of our plant is really rather small. For a 924 megawatt plant, the maximum size of our plant is only about 34 acres, 14 hectares, and it really is pretty compact. It allows for a small emergency planning zone, so it can be built close to points of use. I like Brett's image before of showing the plant right in the middle of a city area, and that's what a goal for SMRs is: a very small planning zone, so it can be at points of use, so you can really leverage multiple capabilities and multiple off-takers. We have our patented triple crown of safety, and we've talked about that a lot. I'll move on. And that develops a second to none safety class, and I mentioned the emergency planning zone. I put this slide in here in the next slide because I think these are some of the most important factors, important elements of NuScale's design. It's not just the design, its ability to integrate with renewables and existing grid technologies while preparing for meeting the grid requirements of the future. That's an incredibly important factor, I think, for any energy source, including small modular reactors as we move forward. You've heard my colleagues talk about being able to provide energy for diverse platforms. I always like listening to Dave talk, because I know Dave, but I like listening to him talk about the ability to meet different market sector needs. And, you know, NuScale took that to heart in developing the overall plant. And the interesting thing about our capability is, with having multiple modules, they can operate either in unison or independently. So I love this slide, and I love to be able to talk about being able to provide energy, clean nuclear energy, to all of these elements and all of these industries at the same time. One thing we don't have on here, and we've been talking a lot with some Nordic countries, and I've talked quite a bit with folks in Finland, is about being able to provide heat for district heating. And that goes back to the comment I made before about having a small emergency planning zone and having the plant very close to points of use. It's hard to move heat and keep it as hot as you need it to be from long distances. So this lends really well to NuScale's technology, and I'd say in general, SMRs in general. But I feel like some of the critical factors are being able to provide clean energy for mission critical facilities. I think we've seen in times of COVID and with natural disasters, I don't want to use the word critical, but it really is critically important to be able to provide energy to those sources while supplying energy to the grid and trying to bring the grid back up so you can get things back running very effectively. One of the things I wanted to note here was hydrogen production. And with one NuScale power module, we got enough energy to produce over 2,000 kilograms of hydrogen an hour. That's an awful lot. So we think we've got a winning technology. We have quite a few opportunities in front of us. We're working with multiple customers and trying to move the technology forward globally. Our primary project is the carbon-free power project that is owned by UAMPS, the Utah Associated Municipal Power System. You may have seen the news that project is moving forward. The agreements are coming into place with Fluor, which is our EPC, and that'll be happening. The target is 2029, but we've built up our capability to be able to deliver in NuScale power modules to go commercial in 2027. So we have that ability, and we're we're moving forward very, very quickly. And hopefully we're bringing all my colleagues along. And that's what I wanted to go through today. Thank you.
Thank you very much, Scott. And thank you everyone for giving these updates. good to see that you're going fast forward with your designs and developments. So, but let's go to the questions. So maybe let's start with the question of the panel discussion. Why do we need SMRs if we already have large nuclear power plants? So maybe let's start alphabetically from Alan.
Sure. So why do we need SMRs if we already have large nuclear power plants? I think part of the answer there is, if you look at what's happening in the Western world at the moment, large nuclear plants are struggling, and a lot of that is down to the fact that they've got huge issues with financing. It takes governments to finance large nuclear power plants. SMRs, certainly we're designing our SMR to be financeable with private finance. So that's the first reason. The second reason is the scale of the challenge here is huge if we want to decarbonise. I think all the panelists have touched on it. We often get obsessed with grid electricity, but we've got to decarbonise the rest of the energy system, and grid is only about 20% of global energy. We need more electricity to do that, therefore we need more flexible power plants, and SMRs can be sited in many, many more locations. So you can put a large power plant, they've got more flexibility and they can work in an energy system, Scott just said, whether it be hydrogen generation or desalination or other aspects. And they can be delivered to a greater number of sites that aren't necessarily on the sea or more inaccessible for very large components associated with large plants. So there's many reasons why SMRs can sit in an energy mix alongside large nuclear power plants, and they have some significant benefits as well. But the key one is that much lower capital cost, lower risk, and speed to build.
Mm-hmm. Thank you. Brett, do you have add to that?
I mean, yeah, let's just be honest. Other than Mark's plant, none of these plants are really small. But I think the key is we need to, like Alan was saying, the problem is the cost. And the problem is when you get into this territory of these super large plants being mega construction projects, and then costs spiral out of control. So I think the key here is, not so much small in size, but small in dollar amount. You got to keep it under $1 billion. If it's more than $1 billion, your project is going to fail, period.
David, any thoughts?
Brett, thanks for the lead. Thanks for the lead in on that. So ours is not as small as Mark's, but the 300 megawatt kind of range fits perfectly in replace for coal. A lot of the Eastern European countries and the demand on coal, that niche fits in there. But you hit it on the head. Cost is the biggest driver. I mean, these mega projects are cost more than lots of countries' GDP. So you have to drive the cost under $1 billion, be competitive with other sources of energy generation that can be financed not by governments, but by private lending institutes. So that's the biggest reason. And the flexibility, as well as what Alan mentioned, I mean, that's key. We need these to replace coal, and coal is used for district heating, coal is used for electricity generation, coal is used for many different things. So we've got to get rid of those plants and replace it with the clean technology.
Thank you. So Mark, you definitely have something to say about microreactors.
Yeah, all reactors are too big. Sorry, guys. Yeah, I mean, it's exactly that. I think we always, setting aside the fact that USNC's focus on microreactors is with a very specific application. We kind of believe that the smaller you get, the kind of laws of physics of nuclear power become reversed, and being really small offers a whole lot of opportunities. I was thinking of Estonia. You're talking a country with about an average demand of somewhere around 1,000 megawatts. So a gigawatt scale nuclear plant is just not, out of the question. Microreactors and by extension SMRs probably have the advantages, the three advantages, that they're cheap, they're quick, and they're economically efficient. And I think we've spoken a lot about the first two, and when I come in with economic efficiency, I think you can get a lot closer to building what you need. You don't overbuild, you don't underbuild, The timing means you can plan. You don't sort of have to estimate 5 or 10 years ahead. And again, one of your biggest costs on a traditional nuclear power plant is your interest during construction. And that's not capital working for you. So anything you do to do that gets you much more economically efficient. And I think that's really one of the things that interests people, prospective off-takers, in using SMRs. Thank you.
Thank you. Thank you. So, Scott, do you have anything to add?
Well, I can't disagree with my colleagues at all. They all hit the nail on the head on cost, size, and time for implementing. And Mark was really right. There are two big things when it comes to implementing any kind of large project, but particularly nuclear. It's the cost of capital, and that comes down to labor. So the bigger the plant and the more complex it is, the more difficult it is to be quick and cost effective. So I really think that it comes to driving for SMRs, driving the ability to implement a plant very quickly. I'll disagree with Brett slightly. I don't think every plant is too big. All right. I think the important thing is to be able to be scalable and to be able to meet each need in an individual manner. Our plant looks big at the outset, but it's very scalable in implementation. We've had multiple customers talk to us about, I want to have the plant built for 12 modules, but I don't want to install all 12 to start. How can I cut back that cost of implementation and leave myself the flexibility to increase my clean energy output over time? Don't forget, a plant is really designed for 60 plus years of life. So every 10 plus years, you want to add another module to increase clean energy to meet your overall demand. That's easily done. So I feel that with SMRs, it's about the flexibility and the cost, not just one or the other. I think they have to come together. That's how I see it.
Thank you. Yeah, so I'd like to continue with that. Before today, there was discussion about the construction time of the SMRs. So what is your plant's construction times, and what do you see? What are the, let's say, success factors or limiting factors on building these plants in a timely manner? Maybe let's start with Scott.
Thank you. So we are currently our target for construction cycle, and we're working through that now. Since we've announced the 4-module and 6-module plant, we're reassessing everything, reassessing the cost estimate and the overall construction cycle. For a 12-module plant, our construction cycle is estimated to be about 36 months. Personally, well, this is being filmed. Personally, I feel it's much shorter than that, but that takes into account a lot of different customer aspects and site requirements that we've seen. So we set a target that kind of covers the whole gamut, but I feel it's much less than that. And so what are the biggest challenges with that? Well, it's it's ensuring the site characteristics can meet the overall need and ensuring there's not a lot of upgraded design or specific design detail. One little caveat I like to put in is we've looked at some of the coal replacement opportunities, and there's some strong opportunity there to really reutilize infrastructure and really cut down the implementation time, like a water intake in that and transmission yard, cut down the implementation time, and which cuts down the labor, the cost, etc. So we think it's about really looking at the overall site characteristics, analyzing that well, and being able to move forward very quickly.
Thank you. So Mark, what about USNC?
Yeah, I think we come from an even more extreme position. And this is really possible because of our really small size. We don't even use the word construction. We talk of produce, deploy. We are focusing on building these these reactors like aircraft, minimizing on-site activity, which means the on-site portion of the activities will probably be completed in a matter of months. This is something we plan to demonstrate at the Chalk River plant. And I would say that's cheating. We're on such a small scale that something like this is possible. But I think that provides a great opportunity to really change how people, I would say, consume nuclear power.
Thank you. So David, what about X300 time schedule?
For our first of a kind, we're looking at 30 months. Nth of a kind is 24 months. The big drivers there are how we are doing the initial construction technique of tunneling versus at large excavation. And one of the key LTRs, licensing topical reports, we have submitted to the NRC is to review that technique, how it's licensed, how do you monitor it, and how do you actually license that as you're putting the module in the ground. And that should be approved by the end of this year, and that will get us where we need to be for the 2-year construction schedule.
Okay, thank you. So Brett, tell us about Open 100.
Yeah, I think we sometimes have to remind ourselves that nuclear isn't special, right? We give ourselves all these exceptions. Oh, things in the nuclear world take so long, but nuclear is not special. It is a power plant, and normal thermal power plants can be built in 18 months. So if your EPC, your engineering, procurement, and construction firm can't promise you 18 months at a fixed cost, fire them.
Okay, good. So, Alan, what about Rolls-Royce?
Sure. So our construction time, we call it 2+2. So the first 2 is for the site remediation, excavation, laying everything up to our aseismic bearing, and then it's 2 years for the module assembly and commissioning on the site. In terms of what's the critical path on that, Brett alluded to this. Licensing is the biggest challenge. The fact that a lot of the associated industries who come on board when anybody wants to build a nuclear power plant hear the word nuclear and think, wow, this is a great opportunity for us to make some money. And as such, we see what are relatively straightforward licensing activities in other industries become huge and complex in nuclear. That's something collectively we have to avoid. If you look at some of the experiences the UK has had, the hundreds of millions, billions of pounds have been spent before they've even put a shovel in the ground. That's something we've absolutely got to avoid. There is no reason for it, no excuses for it, and the nuclear industry is as culpable for getting it wrong as some of the other areas as well. We've got to fix it.
Thank you. So another question. You know, we talked here that in Estonia we are planning to maybe start building 1 or 2 SMRs. But what do you think? How big is the market potential in general if you look at the big picture and the global challenge we are facing? So maybe we start with Alan.
Great. So we think there's huge market potential. As I mentioned before, we often talk about grid power, and we've spoken about the role SMRs can play in the grid. But this is about total energy. If we look at the energy required to make synthetic fuels to replace diesel or jet aviation fuel, or to create hydrogen for district heating, it's a huge amount of energy. So the market is enormous. We sit in the 50 hertz market, so our plant is designed for that 50 hertz grid. It's not insignificant to change the design for 60 hertz. So we're targeting those 50 hertz markets primarily. And it's a huge market. The critical thing for us is proving that we can do what we say we'll do. And the biggest headwind we have is the challenge that nuclear has based on history, the perception that nuclear is always late, always over budget. That's our biggest headwind. Once we've demonstrated that we've removed a lot of those risks and we can do what we say we will, then the market is enormous.
Brett, your remarks?
Nuclear should replace all fossil fuels worldwide, period. The market size is 40,000 gigawatts.
Thank you. That's a lot, yes. So, David, your thoughts?
I agree with Brett. The market is massive. And we're not in it for the 1 or 2. We're in it for the large build out scale production and how you get these out there in the world. It does, and we do need to replace coal and the other carbon generating technologies. So again, we're in this for the hundreds, if not more, reactors, not just the one or two.
Thank you. So, Mark, what about USNC point of view?
Yeah, this is easy for me to answer because I think at our scale, the market is essentially infinite, in terms of numbers of units. That aside, I think I very much agree with what everyone has said. It's the first time I've been working in an area, and I've worked in many, where every year the market projections grow bigger and bigger. There's the fossil fuel electricity market, and then there's the general process energy market, and there's a potential market expansion for hydrogen. These numbers are just really big, and I think that's not the question. In my mind, for us, it's about proving a way to the market, getting into the market. Because at the moment, I could equally answer that the market is zero. There is no market. No one's building any. No one's buying any. And I think everyone on this call has exactly the same attitude here, that we're working very hard to get a first product in the field, and that will enable this market to actually come into existence.
Thank you. Scott, any remarks?
Yes, so I love what Brett said. Actually, I appreciated everything that my colleague said, and I agree with Brett 100% specifically, and particularly what Alan said, that the goal really here is getting everyone is being able to get the regulatory processes aligned so that not so drastically different that nuclear looks very different in every country. This is what Brett said earlier. Nuclear is not that difficult. We understand how to build these plants. We understand how to control the reactivity and everything. And it should be much easier. So, we're going to find out. NuScale has a license. Let's see how attractive that is to other countries in trying to move forward and make the licensing, the construction, and the implementation much easier, leveraging that factory fabrication for repetitive and cost driving down ability. It comes down to manufacture, not building in the field. Manufacture it, ship it, put it in place. And I agree with what Dave and Mark were saying. There's a broad market. Nobody's in it for one plant. That's what some of the big plants used to be for. That's not what SMRs are about, and that's not what the world needs. So we've got to be able to deliver that, but we've also got to work with countries and governments and regulators to move forward and not just look at it from the same old perspective. That perspective has gotten really cloudy over time, and it needs clarity very quickly. Thank you.
Thank you. Thank you very much. Yes, actually, this was a very good lead into my last question to you all. So we know that there are more than 60 different SMR designs in the world, and not many or have been built. If we take maybe exception of the Russian ship nuclear power plant. So what do you think? What are the critical success factors to SMRs really to be the game changer and be the market changer? So maybe let's go from the alphabetical order last time. So Alan, please.
Yeah, so the critical success factors for SMRs, I can't speak for other technologies. For our technology, it's designed to be licensed. So designed for the total life cycle. That means designed to be licensed. It's designed for manufacturing. It's designed for manufacturing the factories, build on the site. It's designed for operation, and it's designed for decommissioning. We've designed it for all the phases of the life cycle to meet the cost and schedule challenges that we have. The critical success factor for us is getting on and doing it. We will demonstrate by doing. We have all the empirical evidence that we can build this, and the time we save, the cost we can. Critical success factor, let's get on and do it. And that's why we're working very closely with our own government now to get on and build them in the UK, where we have a very need and pressing demand.
Thank you. Brett?
Standardize supply chain.
Then short. David.
Yeah, I think design to cost for us is really the secret here. Is how do you make this plant financeable and cost effective for a customer? You know, you can design something that is massively safe and huge, but if somebody's not going to buy it, they're not going to buy it. And so it has to be palatable to the customer base. I think Brett hit it on the head. The supply chain is very important. That's why we're using proven supply chain, proven components where it makes sense. Our fuel is licensed. You know, there's no hurdles to getting our fuel into the plants. So that's a big piece of it as well.
Thank you. Mark.
Yeah, I think you know, my answer is not going to surprise you. It's in line with what I said earlier. You know, we've got to do it. We've got to make sure it's cheap, quick, and economically efficient. And you know, when we've done that, we've basically achieved success. You know, everything else that we're discussing feeds into those core parts of the SMR promise, if I call it that. Thank you.
Thank you. And Scott, please.
You know, it's really difficult to follow these four colleagues. They hit all the intelligent thoughts I had, and then I have to come up with a new one. But I will say that, and they're all right. They're all correct, that there's aspects here that we've really got to hit on and be able to move forward. The one I feel that the biggest aspect, though, is that SMRs and the SMR promise is not some future effort. It's now. It's here. And it's time to start really moving things forward. It's time to start building the first few and make sure that we nail it down and we develop that supply chain and we develop the cost models of each and every one of these designs. Like Brett said before, the market opportunity is huge. There's room for every one of these technologies because they bring something different. And every one of the 60 technologies, they bring something different to each market segment. So it's time to move forward. It's here. It's now. There's no future promise. It's now.
Thank you very much. So I want to thank you all for your notes, for your remarks, and I wish you great success with your design developments in the future, and especially the implementation of the first one. So thank you once again. And now we need to go on.